Good evening, one and all. Can you see my screen?
Yeah, madam.
Okay, thank you. Okay, so let's start today's session, um, which is the eighth live session for basic environmental engineering, pollution and abatement. Now, till last week, we have been discussing on the pollution treatment methodologies, especially like we have started for wastewater treatment. Now, so far, like, can you tell me in brief what are the treatment steps involved in either domestic wastewater treatment or industrial wastewater treatment?
Madam, BOD is there.
Sorry.
Yeah, BOD, bioaxidical.
Yeah,
Yeah, BOD, RO, or
yeah.
reverse osmosis. Uh, these 2 minutes, I know, madam.
Okay, okay, no issues. So, yeah, let me just tell you in brief. Okay, so first step in any wastewater treatment involves preliminary treatment where any uh, coarse material suspended like coarse suspended particles um, coarse materials are removed through bar grates, bar racks, grate, or maybe usually you can say screening, okay? Because this can hinder the equipment, this can damage the equipment parts. Next, we give primary treatment because not all suspended solids are removed in preliminary treatment. So finer suspended solids are removed here in primary treatment. Suspended solids, they are removed. Where we give coagulation flocculation process, then sedimentation, right? So here we try to make the particles or suspended solids bigger so that they are easy to settle and they are then settled into in sedimentation process. Then we can use dissolved air flotation where again suspended particles are removed. Then as you said, there is BOD present in or the organic present in wastewater. Then there we give secondary treatment which majorly removes organic. Right, so particularly the ones which are biodegradable in nature through conventionally used activated sludge process. Then we can have lagoons. Then we can have trickling filters. So till like all these methods we have discussed in detail till the last week. Now we have started with okay, so these are the common or conventional treatment, right? And further, the treatment which will be provided could be advanced treatment and tertiary treatment, where specific to the type of wastewater and the component or the composition, tertiary treatment are selected and provided to the wastewater so that whatever we discharge in the water bodies or the discharged water, it is having quality which is permissible and it is suitable as per the government norms. Okay, so here is again a process where we will be looking into organic degradation, right? So here it is like one of this is a kind of advanced method. okay, or the modification you can say in the biological treatment process. Now, here again, our aim is to convert biodegradable organic matter. Now, the first aim is to convert this organics into carbon dioxide, right? But again, here we are using some electrochemical cell, which will further produce electrical energy or hydrogen, which is again a fuel. So, we are making the process more sustainable. We are making the process more the waste is used to you know generate electricity or fuel, so it is a kind of sustainable process. So if we look into this, then microbial fuel cells are one of the example of it. Now this is the example of a microbial fuel cell. Now it consists of to generate electricity. We know that there is a requirement of two electrodes. One is anode and another is cathode. Now, the wastewater, it goes in here, and there is a biofilm which is there on the electrode. Now, here on coming with like this, uh, biofilm is there in the on the electrode, or it can be in this electrolyte as well. Now, there will be some interaction which results into the generation of electrons, which passes or which completes the circuit. Okay, so if we now the electrons here, the organics, they are converted to CO2 by using the biofilm, and electrons are generated. Now these electrons, they pass through the external circuit which generates electricity, and you can utilize that electricity. So that is a closed loop electricity generation. Now further, there is a permeable membrane which separates anode and cathode. So the H plus which is generated on the this anode side, it can only like this is permeable. This membrane is permeable only to H plus. So it travels, and the redox reaction which is required to uh, happen uh, both on anode and cathode to form a complete circuit. So this H plus will be combining with the oxygen which is taken up from the atmosphere. It will form water. So this is a closed, so here at anode, the organics basically gets converted into CO2. There will be some electrons, sorry. Yeah, so there will be some H plus generation, and at cathode, um, this O2 will accept proton to form H2O. Okay, so a balanced reaction occurs at both the electrodes. Uh, yeah, so now we require some external, either in the form of indirect transfer or direct transfer. We supply the subst the you can say the biofilm seeding indirectly transferred, which is externally generated or self-generated, or there is a direct transfer with the electrode. Okay, so in the case of indirect transfer, either you supply the biofilm seed externally, or it is self-generated inside the cell itself because of some reaction going on, or there could be some direct transfer of electrons with the electrode itself, um, right? So these two type of electron transfer mechanisms happen. Now again, the parameters that define the uh, efficiency of this cell includes the material which you are using for anode and cathode. Further, the efficiency of these material can be enhanced by the use of catalyst. Okay, so catalyst can be coated with cathode or with anode so that its efficiency. Because what is the role of catalyst? Can you tell me what is the role of catalyst? Um, Like, can you give me the general definition of it? Okay. So let me just tell you. Yeah. Okay. Yeah. Can you hear me?
Hello.
Yeah. So can you
Yeah,
tell me
madam.
what
Yes.
is the
Actually, some
role?
here network.
Okay. Okay. No issues. So what is the role of catalyst here? And like in general, do you know the role of catalyst and in any process?
Hello. Madam.
Yeah. Uh,
Gases should be using for boost up the process of the this treatment reaction.
Actually, your voice is not clear to me. Can you repeat?
Madam, catalyst will be using for boost up the reactions in the process
Yeah,
of
boosting the
what
reactions.
what
Yeah, yeah. Okay, you are correct. I got your point. So yeah, basically, catalyst is used to enhance the rate of reaction. Okay, so for any reaction, if we use catalyst, then it is a kind of promoter which boosts or which enhances the rate of reaction. Okay, so maybe if the time taken in the absence of catalyst for the completion of reaction is 10 minutes, then in the presence of catalyst, it will be obviously lesser than 10 minutes, maybe even 1, 2 minutes also. Now, how does this catalyst act? For example, uh, these are the reactants A plus B. Now, they have to form products AB. So, depending on the type of reaction, maybe endothermic or exothermic, it has to cross the energy barrier. Now, this is the energy barrier which it has to cross, where here the intermediates are formed, and this is known as the activation energy of any reaction. So, this much energy is required for the reactants to react and form product AB, right? Now, in the presence of catalyst, this activation energy barrier it is reduced. Okay, so after adding the catalyst, you can say the energy barrier it reduces. Okay, so that is how lesser energy is required in the presence of catalyst, and hence the rate of reaction increases. Okay, so catalysts are very specific. You can choose the catalyst. Okay, so depending on what type of catalyst you are using, the efficiency depends on that. Then the type of substrate. Okay, so here the main aim is to degrade the substrate. Now the degradation or the nature, like how much degradation of this organic happens, it depends on the biodegradability of the substrate. Further, the operating conditions, pH, and the electrolyte which you use, it depends. Okay, because now here you are using microorganisms, right, which acts upon the substrate for its degradation. And there are parameters uh, like temperature, pH, nutrients availability, right? So these parameters they affect the growth of microorganisms. So in a way, pH and the type of substrate which is the nutrient for it, anyway like it indirectly relates the growth of microorganisms and hence the degradation ability of microorganisms and the efficiency, right? So this is how uh, parameters affect the wastewater treatment efficiency. Now, further, we have achieved current generation here. Okay, so we have connected these two electrodes externally, right? So we have made a closed loop so that electricity is generated. Now, in the class, you can see the formulas are derived. I will not be going into deep into it. So, here, depending on the amount of substrate, okay, so amount of organics degraded. Uh, so the amount of organics degraded, it relates with the electrons formed or transferred. And more the degradation happens, more will be the electrons formed, and more the electricity generated. Right? So this there is a correlation depending on the amount of organics which are degraded and the amount of electricity generated. So your aim would be here to achieve maximum efficiency and maximum degradation of the organics using this cell. Now there could be a single cell chamber which is like this. Now there could be some double chamber. For example, this chamber has a node which is connected via a cylindrical tube, and this is the permeable membrane. And again there is a second chamber which is cathode. Okay, so similar to this, you can have single chamber or multiple chamber, or you can, instead of membrane, you can have something like else also for the partition, or without membrane also. So certain type of variations you can have, right? And yeah, so this is all about the microbial fuel cell. Okay, so now let's move forward with uh, okay, so till this point, whatever we have discussed is the advanced secondary treatment process. Okay, so we started with the secondary treatment procedures, including activated sludge process, trickling filters, lagoons, anaerobic digestion, right? So all such type of secondary treatment procedures are nothing but conventional ones. Now there are some advancements made in the form of membrane bioreactors, microbial fuel cell. So these processes are intended to have a more sustainable method, or the one or sequential batch reactors, you can say. So these processes are more sustainable, like it could be in the form of lesser requirement of space, it could be in the form of lesser requirement of external chemicals, or it could be in the form of lesser or better efficiency or lesser contact time even. So any of these parameters, if upgraded or enhanced, then we can say the process is sustainable. So advanced treatment methods that we had seen are kind of sustainable methods, right? Now, once we have looked into this, so after the secondary process, depending on the type of pollutant or contaminant, which still remains after secondary pollutant, secondary treatment, depending on the type of contaminant to be removed, we choose tertiary treatment. Okay, so there are number of tertiary treatments which are like very specific to the particular treatment application or particular industry or sewage treatment plant. So yeah, now let's look into that. So tertiary treatments is the final stage to remove specific pollutants, right here. So specific pollutant is the important term here. And these pollutants, they cannot be separated so far through preliminary, primary, or secondary treatment procedures. Now, this include some inorganics, bacteria, or virus, or some parasites. So, majorly some inorganics or some microorganisms. So, all such sort of pollutants. Um, yeah, further, there could be some organics that are non-biodegradable. Okay, so non-biodegradable organics also could not be degraded through activated sludge process or biological treatment. So in that case, these organics also require some tertiary treatment. So now let's start with the tertiary treatment processes, like there are a number of processes which we can use for treatment of wastewater. So let's discuss one by one. Okay. So first one is the adsorption process. Okay. So adsorption is a surface phenomena, and usually in the industries or in any, yeah, in industries, the conventional adsorbent that is used includes activated carbon. Okay, so why we use activated carbon? Because of its high surface area as well as the number of pores or large number of pores it has. Okay, so if you want to see how activated carbon surface looks like, so there are special, you can, okay, just a second. Okay, so what happens is, see here. So these are the high resolution microscopy images. So all these images, they show the pores of activated carbon. Now, how pores are important? Now, these pores make the active site. Okay, so the surface has some active site. So these pores, more the pores, bigger the pores, easier will be the access of the pollutant with inside. Okay, further, uh, let's say these pores also determine the time required for the removal. For example, uh, yeah, let's say there are two pieces of activated carbon, one and two. These are the pores on the surface of activated carbon. Now, uh, okay, so if we want to remove the pollutant, what happens? There are pollutants which are easily attracted to the surface of uh, this adsorbent through various forces. Okay, so these uh, surfaces, they uh, attract various pollutants through different forces. Okay, through different forces. Now, these forces could be physical force like van der Waals force of attraction, which you name it as physical adsorption or physisorption, and another is chemical adsorption through chemical force of attraction, for example, coordinate covalent bond, etc., which is known as again chemical adsorption or chemisorption. Yeah. So now again, this is a pellet, right? So there are active sites which exerts these forces onto the pollutant. Okay, and now these forces allow the pollutant to bind on this surface. Now there is not, it is not necessary that active sites are on the surface itself, but three-dimensionally, if you look into the pellet, then it is inside the pellet also. There are active sites. Okay. So now if inside the pellet, if you want to see, bigger the pores, easily water will be able to go inside the pores and bind to the active sites. While in case of uh, smaller pores, it will resist the, like it will provide more resistance to flow. For example, if the pollutant has this much size, So the entry will be restricted by smaller pores more as compared to the bigger pores. So due to restriction in mass transfer, which you term as mass transfer resistance, being more or being higher in with smaller pores, the rate of removal reduces. Right? I hope you are able to understand this. Yeah. Okay. So now if we talk about the steps of transport, then there are three main steps for adsorption. Okay, so these pores are nothing but they have some shape. So if I show you a cross section, then let's say this is the surface, then this pore could be of this sort. Okay, so some channel will be there of the pore. Okay, so first, and this is the, let's say, beaker or the tank in which there is wastewater. This is water. So pollutant which is in this water phase. So let's say this is the boundary. This boundary, if we zoom in, so this is the, sorry, this is the boundary between this solid and the water. So there is a layer called boundary layer thickness. So there will not be any change in the concentration till this boundary point, but this boundary, because of the different phases involved, there will be a resistance for or the mass transfer resistance provided because of the different phase involved. Okay, so let's say here the mass transfer resistance is provided. So this is the first step where this is the bulk liquid. So the transport happens from the bulk of wastewater. Okay, so first step is bulk transport, right? Now second step is the internal transport. Okay, so this could be within the pores. Okay, so now there are pores and it has to travel through these pores. Okay, so as I said, the pore size also defines how fast it adsorbs. So second step here involves is first it travels from the bulk of water to this point surface. Then there will be travel through the pore, so which is internal diffusion or internal transport or diffusion, right? And once let's say this is the pore, and if you zoom in this pore, so there will be some active sites in the pores. Now these active sites it will attract the pollutant and there will be some bond formation. So third step once it has gone inside the pore, it will be adsorption, right? So these are the steps involved for the adsorption to occur. Now there are factors that affect adsorption similar to the microbial fuel cell. So these factors include temperature at which the process occurs, concentration of pollutant, the adsorbent amount and the type of adsorbent used, contact time, and the pH of solution. Okay, so um, yeah, why temperature and concentration of pollutant are important? because more the concentration difference, more the concentration difference, or you can say this difference is termed as concentration gradient, because initially if you talk, then the adsorbent has no pollutant, and only the pollutant is present in the wastewater. So there is maximum concentration gradient, and this concentration, more the concentration grade difference, more will be the transfer of adsorption, this pollutant. Now, depending on the type of adsorbent, now there are after activated carbon, and nowadays there are multiple adsorbents that are explored and even used for this case. Okay, so depending on the type of adsorbent, the active sites will differ. And since active site differs, the affinity of that adsorbent for pollutant changes. Now, we need the adsorbent which has a higher affinity for the pollutant, right? Um just a second, give me a moment. Sorry for the disturbance. So, we were talking about how adsorbent affects the adsorption. Okay, so uh, firstly, depending on the type of adsorbent we use, the active site changes, and the affinity of those active sites, they change for the particular pollutant. So, okay, for different type of pollutant that we want to target or that we want to remove for any process, uh, uh, we might use some specific adsorbents also, depending on the process. Further, the amount of adsorbent that we use, that also determines the uh, efficiency of the process. Next, that determines the process is the contact time. Okay. So, how contact time affects? Let's say this is the initial concentration of the pollutant present in water. So initially the amount of active or vacant sites on the adsorbent are quite high. Okay, so all are, let's say this is the adsorbent surface and these are the active sites. So at time t equal to 0, so this is t equals to 0, all these sites are vacant. Now as the time progresses, the vacant sites are used up. Okay, okay, so these are used up. So initially all are vacant, so more adsorption might occur. So there will be a steep decrease. Then as the time progresses, these vacant sites are used up. Okay, so let's say this pollutant has to get adsorbed. So it has to see which active site are vacant. So there will be a time where the rate of adsorption will reduce. Okay, so it has to search for which site is vacant. So after certain point, the rate reduces, and there will be a point where no vacant site will be available. So at that point, you can say this adsorbent has saturated. So this point is known as saturation of the adsorbent. So yeah, contact time, it depends. It is an important factor. And another important factor is the pH of solution, where the pH of solution, it determines the charge on the adsorbent Okay, so there are cases where adsorption process is used for the removal of charged pollutant. For example, heavy metals. Okay, so in these case, heavy metals, for example, lead, it has positive charge. Now, this positively charged lead ions, they are removed electrostatically. Okay, so for electrostatic removal, we need negative charge on the surface. Okay, so this charge on the surface is dependent on the pH of solution, and hence we will prefer the pH of the solution such that it has negative charge so that it will easily attract the oppositely charged pollutant. Okay, I hope you are following. Okay, so now let's move forward. So next is an important parameter which is specific or which is relevant to the adsorbent. So this adsorbent has a theoretical capacity. Okay, so there will be a limited number of active sites on the adsorbent. Okay, so uh, there will be some capacity for the adsorbent to adsorb. Okay, for example, there is a classroom which has number of benches, and each bench allows three students to sit, or maybe two students. Now, so you can say the class has the capacity to accommodate maximum, let's say 60 students. Now it will not be able to accommodate any student which is maybe one or two more, not more than that. So that is the capacity of class. Now similar to that, so here if you compare, so the sitting arrangement, so the accommodation capacity is the capacity of that class. Now similar to that, here the active sites it can absorb the pollutant. Now, once the active sites are used up, the adsorbent will not be able to, like, we will not be able to use. So, the capacity of how much pollutant we can remove using that adsorbent, so we can represent it as the milligrams of pollutant adsorbed per gram of adsorbent. So, this is the capacity or the adsorption capacity or the specific uptake for that particular adsorbent. Now, this is calculated through the isotherm fit, where we use Langmuir isotherm to calculate the specific uptake, which assumes that on the surface of adsorbent, which has these active sites, there is a monolayer formation of pollutant, and there exists chemical bond between the pollutant and the adsorbent. Now, another that we can use is Freundlich isotherm. Okay, so where it assumes that not monolayer but multiple layers of adsorbent it forms, sorry, pollutant it forms on the adsorbent surface. So multiple layers are possible only when there is physical bond existing between the adsorbent and the pollutant, right? So these two you can use uh, to calculate the specific uptake. Now, as I mentioned, that kinetics is an important parameter for a particular adsorbent. So, kinetics is how the concentration reduces with respect to time, and what is the um, order for rate. So, this kinetics will tell you whether it is first order, second order process, and so on. And since rate is proportional to the concentration of reactant. So here the reactants are number one, the amount of active sites, right? And second is the amount of pollutant. Okay, so these two are the reactants because The active sites they attract pollutant, and the pollutant are getting attracted. So these two are the reactants which are binding through physical or through chemical force. So the rate depends either on both or maybe one of them. So depending on that, the rate of reaction could be first order or it could be second order reaction. So the kinetic fitting, it will tell you about the rate of reaction and the order of reaction. Now next comes is the spent adsorbent regeneration. Okay. So regeneration is required when the adsorbent is saturated. Okay. So in industries, the cost of it process increases a lot when you are if the adsorbent is saturated and you are discarding that adsorbent. Okay, so the cost is involved in the terms of using new adsorbent, and further you need to send that you adsorbent which is already used into landfill sites, which also requires some cost for disposal. So it is better to regenerate the adsorbent, which can be done through either temperature variation or temperature gradient. You can use some uh, electrolyte solution or some acid solution, acid or base solution to regenerate the adsorbent. Okay, and once, so what it does, whatever the active sites they are occupied with the pollutant, they are again reactivated. Okay, so pollutant from that active site is removed and it can be further used up to remove more pollutant, right? Now the adsorbent that we use, it can be operated in two modes. One is batch mode and another is continuous mode. So can you tell me what is the difference between batch mode and continuous mode of operation in industries? Okay, let me tell you. So batch mode of operation means that this is the reactor. You dump all the reactants at a time and you allow the reaction to occur for time t, like which is towards completion, and then you take out the products or the byproduct. Now in the continuous mode there will be a continuous inlet, there will be a continuous outlet, right? So there will be a constant reaction that will be going on. So this is the difference between batch and continuous mode. So batch mode it operates on time, while this is a steady state process. So continuous process is a steady state process. Now, usually in industries, the process that we use for adsorption is a continuous process where there could be some different types of adsorption columns used, but fixed bed adsorption column is the most common one. Okay, so how the fixed bed adsorption works? Okay, so let's say this is the column, and there could be either the inlet of wastewater from the top or from the bottom. Let's say we are having bottom to top. This is the inlet, this is the outlet, this is the bed. Okay. So, as the pollutant enters, it will react on the or it will adsorb on the adsorbent. So there will be a particular zone in which it will adsorb because let's say it is having initial concentration Ci. So it has to reduce from Ci to Cf, which could be depending on the permissible limit. Usually, let's say it is zero point 0.1. So here only there will be uh, uh, mm, adsorption. So firstly, it will adsorb completely. So it will adsorb, and this is the zone in which it will get completely reacted, and this zone is completely like this much portion is completely unreacted or unadsorbed. So this is the unutilized bed, and this is the utilized bed. So here the adsorption occurs like this. So this is the uh, like based on some simulations and everything, you can get to know the type of profile it follows. So this is the zone where adsorption occurs, which is known as mass transfer zone where adsorption occurs. And um, for a particular moment, only a particular mass transfer zone will be used for adsorption, while rest portion will not be used. Okay, so here you can say this mass transfer zone is transferring, so in the form of a wave front. Okay, so here let's say initially at this time it is here. Now after some time the mass transfer zone will be here where the adsorption will be occurring, and below this point the adsorbent has saturated, and above that point is unutilized bed. Okay, so this is unutilized bed after some time. So there will be a point where now this mass in the mass transfer zone the adsorption occurs like this. Okay, so the profile is like this. That is a theoretically known profile. So once it reaches towards the end of the bed, okay, so let's say till this it is completely saturated and only last mass transfer zone is remaining. So after certain point, whatever is coming out, there will be, sorry, there will be um, the concentration. Okay, so till some point the concentration is zero. After certain point, the concentration of pollutant rises. Why? Because so this rise, which is above the permissible limit of that pollutant, is known as the breakthrough point or breakthrough time. So after that point, the entire bed has saturated, and that point is known as breakthrough point. So now there will be some region which is unutilized. So that is the final length of unutilized bed, because let's say this is the mass transfer zone and this is the concentration profile here. So S is the concentration profile which is followed, and this is the midpoint of it. Now see, after this point the concentration appears. Okay, so that concentration, so this region of adsorbent will not be used, and so mtz by 2 will be the length of unutilized bed theoretically or in ideal scenarios. And after the breakthrough point the concentration shoots up and it reaches finally the initial concentration Ci. Okay, so this curve is known as breakthrough curve, right? And the time at which the breakthrough point is obtained is known as the breakthrough time or the breakthrough point. Yeah. So this was now there are equations from which you can calculate the length of unutilized bed and the breakthrough time and concentration. Okay, so these equations you can look into the class. Now another type of process that we can use for the removal of the tertiary treatment is the ion exchange. It is a kind of process where we remove the hardness of water in the form of Ca2 plus Mg2 plus by reacting it with a resin which has, let's say, RNA plus, it will react with Ca2 plus or maybe Mg2 plus to form R2Ca. Now here the valencies are different, so such stoichiometry will be followed. And similarly, it can be used for anions as well. And again, the fixed bed column is used for ion exchange resin, where this is the column. Okay, you pack the material here, you allow the water to flow maybe from bottom to top or top to bottom, any way it is fine, depending on the requirement. And here the ion exchange occurs. Now, to regenerate this, specific process is used. For example, if you want to regenerate the R2Ca, so you can add NaCl, for example. So now this Na will replace this Ca to form RNA plus you can have CaCl2 formed again. Okay, so there will be exchange of ions, which is known as, and hence the name suggests it is ion exchange process. Okay, so now let's move forward with another process, which is membrane filtration, which is used very commonly and frequently in industries. Now, these membranes are nothing but a flat sheet, or it could be some another, uh, you can say, this wire sort of thing or fiber sort of thing. So, they are thin and porous sheets now, which can be molded into some flat form or maybe some fibrous form, right, like this. And these membranes, they are nothing but they provide a barrier to flow for the particles or for any pollutant. Okay, so these membranes are like in the case of adsorption, there was some physical force or chemical force which caused the binding of pollutant with the adsorbent surface. Now, these membranes they have pores which show size-based separation or some repulsion because of the ionic charges or some concentration gradient which results into separation. Okay, so let's say this is the membrane surface. So it will have pores on its surface. Now, whatever the pollutant which is having, let's say this is the size of one pollutant and this is the size of another pollutant. So this pollutant will easily pass through the pores, okay, because its size is smaller than the pore size. While this particle is much bigger than the pore size, so it will be restricted to pass. So membrane will hinder the path or hinder the flow of particles which has higher sizes as compared to its pores, where you can say this is nothing but the size-based separation. Now, there are membranes, as you mentioned, that the membranes like RO membranes. So these membranes are nothing but dense membrane. Now, what does dense membrane mean? Dense membranes. Now, dense membranes are nothing but there are nanometer sized or less than nanometer sized pores, or you can say no pores. Okay, so whatever transfer occurs here across the membranes is because of only the concentration gradient, which results into mass transfer to occur through diffusion. Okay, so here that is nothing but the example of reverse osmosis RO. Now, RO you would have heard every now and then because every household nowadays has RO for the purification of water, right, to make it drinkable. Now, there could be some ionic charges which could show some separation. Okay, so depending on the charge, it can have a charge effect or Donan effect, you can say. So the let's say this is the membrane surface which has positive charge. Okay, so this is the direction of water flow. Now, whatever will be the negative charged pollutant or particle, it will pass through, while whatever will be the positive charged pollutant, it will get repelled because of the charged membrane and it will pass. Okay, so because of the electrostatic repulsion, not attraction, repulsion exists here, which causes the pollutants to uh, be removed. And another type of membrane where temperature plays an important role is membrane distillation. So these membranes are permeable not to pollutant but to water vapor. Okay, so let's say this is the cell which is separated by a membrane. One will have temperature higher temperature HT. Another will have cooler temperature or lower temperature LT. So at higher temperature, there will be more water vapor generation. So partial pressure of water will be more here, and the water vapor here will be much lesser. So there will be a gradient in the amount of water vapor which is present on each side, which causes the water vapor to pass through. Okay, so firstly, the water is vaporized and it passes through the membrane. Okay, so this membrane is only permeable to water vapors, and here on the cooler side it uh, goes, and where it condenses and we can have pure water obtained. Now this membrane which we are using here, it could be of multiple material or various materials we can use uh, to synthesize membrane. Now these membranes could be organic membranes or inorganic membranes. So organic membranes nothing but involve polymer for polymeric material to form membranes, and inorganic could be, let's say, Al2O3. So these are nothing but metal based oxides, okay, which are nothing but inorganic membranes. So these have different properties. For example, polymeric membranes, they are less like polymers, they degrade very easily, so they are having lesser temperature resistance. So at higher temperature, these polymeric membranes, they won't be they cannot be used. While inorganic membranes, so you see Al2O3 or similar membranes. So ceramic membranes are also another name of inorganic membranes. So these membranes, they are sustainable, not sustainable. They are susceptible to higher temperatures as well. They do not get degraded or their structures do not change at higher temperatures. So depending on the polymeric material, you have various drawbacks and uh, various advantages uh, for that case. Now there are important. Let's understand how the membrane works. So let's say this is the membrane surface and this is the feed. So there are two multiple types of modes in which membrane works. One is dead end mode. So one is dead end mode. Second is cross flow mode, which are very common. Now, out of these, cross flow is one of the most common because what happens in dead end, you are entering the feed through this. Okay, so blockage of pores will be much higher. While in the case of this, the feed passes in this direction, like this is the membrane. So feed passes this way, and the membrane has pores. Now this there will be some pressure applied, so the membrane will have some the pollutant will be permeable to only water and some uh, particles which are smaller than the pore size. So that water will be coming out through these pores, and feed will after the separation it will go again out. So this is known as the reject or retented stream, while this is known as the permeate or permeate stream, which is pure water or purified water. And these membranes are nothing but known as the barrier, which provides hurdle for the pollutant to pass through, right? So now the reject stream which is coming out, it will have more pollutant because the pollutant has not gone anywhere, but the amount of water uh, which was there, it has reduced. Okay, so concentration of pollutant is much high than feed in retented, right? Because pollutant is not going anywhere. You are just making two streams, which is one is having higher concentration, another is having lower concentration. So you can use the ones which has lower concentration, and that is the permeate, and you can recycle that water. And this can be later uh, converted, sent to zero liquid discharge for separating, converting into the particle or solid form, which you can send it to landfill sites. Now, to accommodate this membrane, there are various modules which are used. So, one is tubular module, another is uh, hollow fiber membrane, another is spiral wound plate and frame. Okay, so I have shown the images of all. So, uh, let's say this is the tubular membrane. So, this tubular membrane has the membrane wound in the form of tube, and it is supported again by a bigger tube. Okay, so the feed water it goes inside. So this is the direction of feed water, and the water permeate, it goes outside this membrane through like this. Okay, so let's say from inside the feed is passing. So from inside, after the end of the at the end of the tube you will have reject stream, and outside in the annular space you will have permeate or clean water stream. So here the flux is more and it is easier to clean comparatively because there are bigger modules or bigger components involved. Now another could be the hollow fiber membrane. Okay, so hollow fiber, these are uh, these are fine uh, fiber structure. So let me show you how these looks like. So, yeah, see how compactly it is. Sorry, the image is not clear, I guess. Yeah, see how compactly it is packed. So, each of this, if you zoom in, yeah, so each of this thread is a fiber, which is the membrane, right? And if you see this like the cut portion, so uh, so if you zoom in, so this has structure like this. So there is a hollow space inside that fiber, and this is the membrane structure. Now, to purify water, you can have two types of feed entrance. One is through the inside of the hollow fiber membrane or the outside of the hollow fiber membrane. So there could be two inlets possible. Now, if the feed water goes from this inlet, the water will come out in the annular space and vice versa. You can have. But you see this hollow fiber membrane, they have very small dimension. Okay, so in this case, the flux is very small. Okay, so the amount of water that you purify is like very small amount of water it gets purified. But you use thousands of hollow fiber membranes at a time. So that is how you increase the uh, flow rate that you can purify. Further, this hollow fiber membranes, because of their small dimensions, they have high surface area. So efficiencies in this case is much higher as compared to other modules, right? So this is one of the advantage. Now next is spiral wound membrane. Okay, so in the spiral wound membrane, what you are doing, you have a support. Okay, so let's say there will be a support rod and which is having free space. So this is the free space of that support from which feed will pass. Okay, so feed will pass and membrane is rolled over to that support. Okay, so you roll the membrane. In your houses also you would have seen RO membranes which are packed inside a tube, and if you take out you will have a compactly packed RO module. So that is nothing but a spiral wound module. So in that case, again, if this is the membrane, so there are spacers used. Okay, so these spacers, what they are used for? They are used for equal or uniform distribution of feed water across the membrane. Now these after permeation, okay, so feed water it passes like this, and water it travels like the barrier it crosses, and the permeate water it passes in this direction and it is collected later. Okay, so again there are permeate spacers also used so that the permeate flow is also having some direction to flow. Okay, and the last module that is used for membrane based separation is the plate and frame module, where let's say this is the membrane and this will be a spacer. Okay, so in between these two the feed will be passed. Okay, so feed passes and the permeate will flow uh, uh, out of the membrane and later it is collected, right? So that's all for the membrane. Now let's talk about another type of advanced or the tertiary treatment method, which is nothing but advanced oxidation processes. So, advanced oxidation processes are nothing but used specifically for the ones where organics are non biodegradable. So, degradable. So, in case um, if you have already removed biodegradable portion in of organics through secondary treatment, so whatever is remaining you need to remove those organics as well, but they are not degradable through any organisms. Okay, so microorganisms they fail to degrade those uh, organics. So can you name some of those non biodegradable organics which could not be removed through this secondary treatment? Can you name them? Yes, Manas. Can you name a few organics which are non-biodegradable? Okay, so let me give you example. Nowadays, pharmaceutical industries they are doing further insecticides, pesticides. There are more and more drugs getting used. Now these are nothing but organics, but they are newer compounds, so they are not so the microorganisms they are not susceptible to them, and hence they are not degradable by using microorganisms. So in that case, what you can do, you can have uh, use advanced oxidation process where you are using some chemicals for the oxidation of these non-biodegradable compounds. So here what you use is the hydroxyl radicals. Now hydroxyl radical is OH dot where you have one like this is the radical, and these free radicals are nothing but highly energetic and short-lived, which uh, can easily react with any of the compound. Okay, so we are using the reactivity of this short-lived hydroxyl radical for the oxidation of the pollutant. So this hydroxyl radical they can be generated by using H2O2. They can be formed from ozone or through UV. Any of the any of this can be used to form hydroxyl radical. Um, so let's say H2O2 is there. So this H2O2 will form uh, two hydroxyl radical. Okay. So there is OO bond to which hydrogen is attached. So there will be a cleavage of this bond, which will result into two hydroxyl radical formation. Okay. Now, if we talk about ozone, then it has O3 molecule. It is a O3 molecule. Now it gets converted like there are multiple steps involved in this. You can look into these steps in the class, but I will give you the overall view. So O3 it is forming O2 plus hydrogen radical. Okay, so water will be there, and if you supply ozone in that, so O3 will get converted into oxygen and the hydroxyl radical. So the steps involved in this process they are nothing but the formation of hydroxyl radical. So first this is formed. Now it attacks the pollutant. Okay. So let's say it CXHY OZ. This OH radical it acts upon this molecule. Now it is not necessary that or in any industry no reaction is single step. There are multiple intermediate steps involved, and especially this free radical action on any organics, there is a chain reaction taking place. Okay, so this OH radical it attacks first the breakdown of this organic. So there are multiple or n steps occur, and which finally results into formation of uh, the oxidized product, which is CO2 and H2O, right? So, which is nothing but subsequent attack and the mineralization to form the final products. Uh, yeah. So now this O2 OS radical formation, it can be achieved using multiple chemicals and multiple methods. So depending on that, there are multiple types of advanced oxidation processes. So first is UV plus H2O2, where UV light, okay, so these are highly energetic or high energy electromagnetic radiation, which causes the breaking of bond and the free radical formation very easy. Okay, so here if you supply UV to H2O2, as I mentioned, two oxygen radicals will be formed by using one H2O2. Okay. Now this OH radical it acts upon the organic and breaks it down. Now another way of supplying OH radical is by supplying HOCl. Now this HOCl it breaks down into OH radical and Cl radical. Now one of the important parameter that is important here is the oxidation potential. Okay, so what is oxidation potential? It is the tendency how fast or how efficiently that compound or that radical is able to oxidize. Okay, so here we use the one which is having highest oxidation potential. Chlorine also is a radical, so it also oxidizes, but the oxidation potential is much lower as compared to OH, which is having highest. So for OH, it is the highest. So both of them they oxidize the organic compounds. Can you please give me 1 or 2 minutes? I will just be back uh, in 2 minutes.
Okay, ma'am. Okay.
Yeah, thank you. So let's start. Okay, so we had discussed uh, the use of HOCl, right? Now, I use my pen not working. Okay, so here in ozone, again, as I had mentioned, that O3 molecule is converted to O2 and one oxygen radical. Sorry, not oxygen, hydroxyl radical. And this process can further be enhanced by providing some extra energy through UV radiation or sonolysis, where you are providing ultrasonic radiation or uh, the sound waves. Okay, so these are highly energized radiations. And next is phenton oxidation process. So this phenton oxidation process uh, is nothing but it uses Fe2 plus and H2O2, which forms Fe3 plus and OH radical. Now this again Fe3 plus, it reacts with another hydrogen peroxide molecule to form Fe2 plus back. So by using all these chemicals, what we are doing, we are just generating ways, generating OH radical in different ways. So overall, if you see this reaction, it requires the supply of Fe only one time, while you need to supply peroxide frequently because it is consumed, while Fe is not consumed at all. So you can say H2O2 is only giving you this OH radical, which further acts upon uh, the organics. Now, the reaction mechanism is highly complex for the degradation using OH radical, right? So, next is the photocatalytic oxidation, where you will be using catalysts which are active, photoactive. So, let's say any semiconductor, okay? So, it has this valence band and this is the conduction band. So this energy gap, so whenever the electron transfers from valence band to conduction band, so there will be a hole formation here, and electron it gets transferred to conduction band. Now this electron it converts this oxygen or water molecule to form OH radical. Okay, so now this transfer of electron into conduction band, you require UV radiation because it has high energy, which is sufficient for the transfer of electron from valence to conduction band. And then this hydroxyl radical, it further acts upon organics to form CO2 and H2O, right? So this is how the oxidation process occurs uh, in the case of uh, photocatalytic oxidation. Now, can you tell me why are we using these type of semiconductors for this process and not the conductors and the insulators? Why? What is its role? Okay, so in the case of this, the okay, the valence band and like the energy difference between conduction band and the valence band is highest for insulators. It has highest difference between conduction and valence band, which means You need to have more energy to be supplied for insulators for exciting the electrons, which is intermediate for semiconductors and least for conductors. So, insulators, they are even difficult to excite in the presence of UV light as well, that is why we focus on semiconductors because we cannot uh, keep every time the conductor active. Okay, so we need to have certain control in our hands where we can keep the material active only in the presence of light. So that is why we use semiconductors. And another is the light driven process where we supply light in any form, maybe UV light or visible light, for the process to occur by supplying some ozone or H2O2. And that is nothing but light driven process, which forms the free radicals and it acts upon the organics to uh, cause degradation. Right, so now that's it for the brief. Now let's move forward for the assignment. So this is the sample assignment for week 8 classes. So first question is the bioelectrochemical system converts cellulose derived carbohydrates and other biodegradable organic matter to produce dash. Okay, so here the key term that you need to see in the question to answer this is the bioelectrochemical process. Okay, so bioelectrochemical process when used for um, the degradation. So electrochemical is nothing but either conversion of a chemical through reaction to form electricity or using the electricity to you know to have a chemical reaction. So in this case, we are generating electricity firstly. Now there could be anaerobic digestion occurring. So we can have methane formation or even we can have in the microbial fuel cells. There are special cases where we can have hydrogen generation also, which is again a fuel. So hydrogen and methane, they both are fuels which we can use later. So, this is a very sustainable process, but they are very difficult to operate also. So, the all of the above is the correct answer for this question. Yeah. Next is which of the following material is or are used as electrodes for microbial fuel cell? Now, as we have discussed that electrodes are is one of the major component in the microbial fuel cell which defines its efficiency. Okay, so depending on the requirement, there could be various types of electrodes available, and graphite, carbon cloth, or reticulated vitreous carbon, they all are nothing but types of electrodes they are used. And you see here, there is a common thing. Each of these is they are carbon only, but in different form. Okay, so carbon based electrodes are the most common one which are used in microbial fuel cell. So D is the correct answer in this case. Now, next question is which of the following parameters affect the operation of microbial fuel cell? Okay, so can you tell me? This is a very simple question. Yes, Manas.
Ma'am, please, I would like to see questions once.
Yeah, yeah, sure. Yeah, which of the following parameters affect the operation of microbial fuel cell? Is it electrode material or the pH or the catalyst or all?
Ma'am, last one, all of the above will be correct.
Yeah, yeah, yeah. You
Elect-
are very
yes,
correct.
yes,
Yeah.
ma'am.
So electrode, it defines the the reaction taking place. So electrode material, then pH buffer and the electrolyte. So these pH and the electrolyte, uh, at pH the microbes, they have different efficacy. So that is how pH also affects the overall process. And also the catalyst, because it can enhance the rate. So for microbial fuel cell, all of the above is the correct answer. So all these parameters, they affect the process. Next question is, the zero charge potential of the adsorbent helps mostly to understand the effect of dash. So first option is the pH on the adsorbent process, temperature on the adsorbent process, contact time, and the pollutant concentration on the process. So do you know the answer? Okay, let me tell you this answer. So, um, the answer to this question, for that, let's first understand what is zero charge potential. Okay, so the key term here is the zero charge potential. Now, this question is for the adsorbent. So, let's take the example of adsorbent. This is the surface of adsorbent, and this is the solution in which it is dipped, right? So, depending on the pH, let's say pH is 3, it will have, so pH determines the amount of H plus and the OH minus concentration in the solution, right? So pH is nothing but minus log to the base 10 hydronium ion concentration, right? So this is the uh, formula for pH. So this pH determines the H plus concentration. Now let's say this adsorbent has some inherent surface charge. Okay. Now at various pH, now if we compare pH 3, 4, 5, 6, 7. Okay. So at every pH, the concentration of these will be different. So at lower pH, more H plus will be available, and there are chances that more H plus they will uh, sit on the adsorbent. Okay, so surface will be uh, positive. Okay, so positive zeta potential, you can say the potential on the surface will be positive. Okay, so positive charge will result into positive potential on the surface, positive charge on the surface. Now, as the pH increases, the amount of positive charge reduces because lesser H plus adsorbs. Okay, so as pH increases, sorry, lesser H plus and the positive charge, the amount of positive charge, it reduces. Okay, so positive charge reduces. Now it reduces, and further after certain pH, because of the OH also available, the surface becomes negative. Surface becomes negative because H plus are not sufficient to neutralize the charge. Okay, the surface becomes positive. So there is a transition from positive charge of the surface to negative charge of the surface, which is nothing but defined by the potential of surface or the adsorbent. Now, the zero charge potential is nothing but there is a transition. You see the transition from positively charged surface to negatively charged surface. So there will be a point or there will be a pH at which surface is negative. Sorry, the surface is having no charge. So that point is nothing but known as point of zero charge. Okay, pH, ZPC. Now, adsorption process is highly used or it involves highly electrostatic force of attraction. So, for example, my pollutant is P, which has positive charge. So, for electrostatic force of attraction, I need the uh, surface to be negative in charge. Okay, so as we have seen that pH highly determines the surface charge or the surface potential. So, we need a point or we need to know a point uh, where the surface will be negative because electrostatic attraction will be dominated. So for that, if we know the 0 point charge, so for any pH less than pH ZPC, positive charge will be there, and for pH greater than pH ZPC, surface will be negative charge. So in our case, where we have positively charged pollutant to get attracted to the adsorbent surface through electrostatic force of attraction. So for attraction to happen, the surface needs to be negative, and for that pH should be greater than point of zero charge. So this point is nothing but zero charge potential of the adsorbent. It helps in mostly understand the pH effect on the adsorption process, right? So this is how you understand the effect of pH on the adsorption process, right? I guess it is clear. So the answer to this question is pH on the adsorbent process. Manas, is it clear?
Yes, sir.
Oh, thank you. Yeah, so next question is for a particular adsorption process, the adsorption capacity or the specific uptake of an adsorbent is determined through dash. Okay, so specific uptake is nothing but it is equals to amount of pollutant adsorbed in milligrams per gram of or the amount of adsorbent in grams, right? So for that, you need to do experiments which requires equilibrium study. Okay. So what you do in this experiment, you choose different initial concentrations for say C1, C2, C3, C4, and C5, right? And then you uh, calculate for each of these concentrations, initial concentration of pollutant, to calculate the final concentration C1F, C2F, C3F, C4F, and C5F. Now you calculate how much pollutant has been removed for each of these concentrations, and you have a plot on amount of pollutant removed and here you will have initial concentrations So you will have a plot like this. So you for this experiment, you allow infinite time, or it not infinite time, the time to achieve equilibrium. Okay, so these are nothing but concentrations which are equilibrium concentrations, from which you will get a similar plot. And now after this is saturation. Okay, so here you fit Langmuir isotherm. Okay, so Langmuir isotherm, which will give you the uptake capacity. So, okay, so this uptake capacity is nothing but theoretical value, which is the maximum amount that can be removed. Okay, so for which you need to do experiments which are equilibrium in nature. Okay, so it requires equilibrium to achieve. So it is an equilibrium study. I guess it is clear to you. Okay, so for this, the correct answer is equilibrium study. Next is the pore size of the membrane required for microfiltration is dash. Okay, so I guess I forgot the point to discuss. There are multiple types of membranes, and these membranes are divided based on the pore size that is there on the membrane. So first is microfiltration, which is having the highest pore size. Then comes ultrafiltration, which is having somewhat lower to microfiltration. Then is nanofiltration, and last is reverse osmosis. So from this direction, the pore size reduces. Okay. So here, like it is not the way to answer correctly. Like you should not select blindly that any the one which is having highest pore, highest range will be the answer. That is not the case. You need to look into the pore size range, and then you need to answer. So this is the range in which the pore sizes are there on the membrane surface. So here we are asked about this microfiltration. So usually it has the pore size which is in the range of 10 to 0.02 microns. Okay. Next question is, from the figure given below, identify the polymeric chain. Okay, so you need to tell what is this polymer. Okay, so this is a fluorine based polymer which is used for synthesis, or which is used as a material for the membrane uh, synthesis. So, do you know what it is? Okay, so it is nothing but you need to remember it is nothing but polyvinylidene chloride. Okay, so it is having a vinyl monomer which are saturated through fluorine. So it is, and which is polymerized, so which is nothing but polyvinylidene chloride. Now next is a numerical which we need to solve. Okay, so let's read the question. So find the water flow rate in meter cube per meter square day. So which is nothing but flow rate per unit area. Okay, when it passes through a porous polyethylene membrane by a pressure differential at 70 degrees Celsius. Now the porosity of the membrane is nothing but 30%, and the diameter of pores is 0.5 micron. Okay, so D here is given to you as 0.5 micrometer. Tortuosity tau is nothing but 2. Porosity is epsilon, which is zero point 0.3, and P naught is the pressure on the feed side, which is 400 kilopascals. PL is the pressure on the permeate side, which is 100. kilopascal. Now assume the membrane to be 2 micron thick. So Lm is 2 micrometer, 2 into 10 to the power minus meter, with flow being fully developed. Uh, Assume the viscosity to be 0.42 centipoise, or that is equals to 0.0002 42 pascal into seconds, and the density to be 1000 kilogram per meter cube. Okay, so you need to find here flow rate per unit surface area. So for which you can directly use this formula. Okay, so put up all the values. Epsilon to you is given as zero point 0.3 into D is given to you as zero point 0.5 micron, which is zero point 0.5 into 10 to the power minus 6 square, and into P naught is 400 minus PL is 100. Now these are in kilopascals, so you need to multiply it with 10 to the power 3 to convert it into pascals. Next is 32 denominator. Viscosity is 0.0042 into Lm is 2 into 10 to the power minus 6, with and tortuosity is 2. Please calculate. Are you getting? Yes. Could you get the answer? So this is the way you will solve it, and the correct answer to this question is option B. Please solve it and let me know when you are done. We will move to the next question. Which of the following is are the example of advanced oxidation process for water treatment? So let's look into the option, which are phenton oxidation, photocatalytic oxidation, and the ozonation. So advanced oxidation processes are nothing but the ones which are used to synthesize OH radical in various forms, and that is used for the oxidation of organics. Now here, if you look into the options, all these options, they are the methods which are used to generate oxygen hydroxyl radical in different forms. So they are very, like it uses various chemicals in the form of catalyst or in the form of ozone or in the form of penton reagent, which at the end synthesizes or forms hydroxyl radical, and hence it will be used for oxidation, right? So all of the above is the correct answer. Now next question is 100 ml solution containing 25 milligrams per liter fluoride is treated with adsorbent dose that is equals to 5 gram per liter. Now the percentage removals of fluoride were 70%, so the specific uptake is nothing calculate. So to calculate specific uptake, what you need to do, you need to first write down. Let me show you the formula. So formula for specific uptake is equals to uh, concentration initial minus final concentration of the pollutant divided by, which is in milligrams per liter, divided by the adsorbent dosage in gram per liter. Okay. So if you don't know the adsorbent dosage in gram per liter, so in that case you can use this formula, other formula, which is Ci minus Cf into the volume of solution in liters divided by the mass of adsorbent, which should be in grams. Okay. So you need to maintain the units to get the answer of specific uptake in milligrams per gram, right? So let's put up the formulas here, and we are given the adsorbent dosage in gram per liter and the concentration in milligram per liter, which is convenient to us. So now let's put up the formula. So we know Ci, which is 25 milligrams per liter, and Cf will be, so here 70% is removed. So what is remaining is 30%. Okay, so zero point 0.3 times 25. Okay, so calculate this, and the dosage is nothing but 5 gram per liter. So now if you put up the formula, so 25 minus zero point 0.3 into 25 divided by 5. Okay, so you can take out 25 common, so it will be nothing but 25 into zero point 0.7 divided by 5. Now you can solve this, and what answer you will have is 3.5 milligrams per gram. Okay, so unit here will be since mm, yeah, since the concentration is in milligrams per liter and the adsorbent dosage is in gram per liter, so liter will get cancelled out, which will give you milligrams per gram. Okay, so that is how you calculate the specific uptake. Okay, I hope it is clear to you all. Um, Miss Manas, is it clear?
Yes, ma'am. Yes.
Okay, okay. So, yeah, that's it from my side today. This is the end of sample assignment for week 8. If you have any doubts, you can tell me, or else I will end the class here. Okay, so I guess there are no more doubts.
Uh,
Uh, you were telling something?
No, ma'am, no.
Okay, okay. Yeah, so thank you everyone for joining. That's the end of um, today's class. We'll meet again in the next class on next Tuesday. So I will end this class. Thank you for joining. Thank you.
Thank you, ma'am.